is not the only factor of influence. And that is not taken into account in this approach. For that reason, there is a third type of approach, which is called the joint probability method. And in that approach, you take all these factors that are contributing to the discharge of peak water levels, you take them all into account. So that could be forced rainfall depth, which also look at the spatial distribution of the rainfall, take into account initial conditions of the soil, you take reservoir volumes into account, ocean water levels, anything that you think it might be relevant to the output you're looking at, you take it into account. It also means that for each of these factors you need to derive your statistical features up front. And that's also why this method is called the joint probability method. Right? So you look at the joint probabilities of the different factors. Now let's give an example of how that works. One from the Netherlands, but this is a situation that often is relevant here in Australia as well. It's when you look at the tidal river, so we have the influence of the seawater levels, or in Australia of course ocean water levels, and river discharge. And you can imagine if you look at this location, the local water level, here, the local water level at that location is influenced by both the discharge and the seawater level, and you can kind of you can show it in a contour plot like this one. So on this axis you have the river discharge, on this axis you have the seawater level, and here these lines show the level, the local water level at that location. And what you then can see is that an increase in the discharge will increase the local water level, but also increase in the seawater level, and that both have an influence on the local water level. And these kind of contour plots you usually can derive those with models or knowledge of how the system works. This forms a good basis of the joint probability method. Now let's assume for example that at this location flooding starts at a level of 4.5 meters above the reference level. That would mean that all the events that are shown here in red are essentially flood events. So those are all the combinations of river discharge and seawater level that lead to a local water level above 4.5 meters. So those are the events that we are particularly interested in, because in this case we want to derive what is the probability that a flood occurs at this location. So that is the first step. So we need to identify all these events. Well, in this case we already done that. That's because we got these nice contour lines available. In most situations you start from zero. You need to start doing model simulations to actually locate this area. So that's the first step. And then the second step is, of course, to determine the probability for each individual event. And there are several potential events in there. For each individual event, you determine the probability, and in the end, you take the sum. Because then you have all the events that lead to flooding, you sum the probability of these events, that gives you the total flood probability. Now, that sounds still a little bit vague, probably, so let's again give a similar example. What have you done to this thing? You defeated it.
Just giving a good refresh of
Yeah.
what's been going on.
Yes. So we're going back to our example of the two dice. It's just an analogy just to understand a little bit the steps involved in determining this probability. So suppose you play a game and your opponent can win the game by throwing 10 or more. So then you can imagine that those are unwanted, undesired events, and if you want to gamble on this game, not sure if that's allowed in Australia, then of course you want to know what is the probability. So first thing you do is identify the events, in this case, that are undesired, and in this case all the potential combinations that lead to a throw of 10 or more. So that's step one. And step two is you start to compute the probability. So what we have here is 6 undesired events. And each of them has a probability of 1 in 36, because there are 36 combinations, and each of them has an equal probability. So in this particular example, we have a total probability of failure, or probability of losing the game, of 6 divided by 36, or 1 over 6. It's very, I hope, relatively simple example, but I hope you can already see sort of the analogy. Yeah? Consider this guy to be river discharge, and that one to be sea level. And so these are kind of steps that you take. In this case, we can compute it just on paper. Unfortunately, in flood risk analysis, it's slightly more complex. And there are several reasons for that. One of them being that often you have more than just 2 variables. So you have a lot of combinations that you need to look at. These can be correlated. Often, for instance, high ocean water levels coincide with high rainfall. You need to take that into account. You have continuous variables like river discharge instead of rise, which only has 6 discrete outcomes. But most important of all, a dice is a relatively simple process. You just roll it. But when you look at the catchment, you have all these processes: hydrology, hydraulic, and you need to model those. So that makes it much more complex. And that causes that you cannot simply compute your probability on a piece of paper. You actually need some more advanced estimation techniques. And those are the joint probability methods. And there are several techniques to do that. I won't go into detail all of them, just mention that there are more techniques, more than just one technique. The reason is that what I often see in literature is that the terms joint probability method and Monte Carlo are mixed, as if they are the same. They are not. The Monte Carlo method is just one example of a joint probability method. So, but nevertheless, I'm going to zoom in on the Monte Carlo method, also because that's the one that we are applying in the Brisbane River study. So how does it work? Well, in essence, it's very straightforward. So what we do in this example, again with river discharge and sea level, what we do is first we derive the statistics individually by deriving those histograms again. And from that statistics we start simulating. So we take samples from the probability distributions that we know. And that is also quite straightforward. So each dot that you see here in this picture is a combination of the seawater level and river discharge that have been sampled. And we do that many times, repeatedly. And in the end what we do is we count the number of times that this water level that we are looking at is exceeded. Those are depicted here in red. And I need to emphasize here, I'll show you the blue line, it's kind of the border between the two. In reality, of course, you don't have that, but this is just for visualization. In reality, the only thing that you can do is do those simulations and see which individual points lead to an exceedance of 4.5 meters, the red ones, and which one don't. Now the Monte Carlo method, once you've done this, it's very straightforward. What you simply do is you count the number of exceedances and you divide it by the total number of samples. And that gives you the probability of exceedance. It's really that straightforward. However, what makes it less straightforward is this whole sampling process. And we'll discuss that a little bit more when we discuss the Brisbane Catchment study. So this is in essence the idea of the joint probability method, in this case Monte Carlo. And so you take the 2 probabilities jointly into account. Now let's see how this works again on an academic example, one that we know the answer, because then it's good to see we can compare how this method works on a case from where we already know the answer. So what we see here is 1/4 of a circle, quarter circle, with a radius equal to 1. And perhaps you remember some years ago that the surface of the full circle is equal to pi, the product of pi and the square of the radius. And in this case we have a radius equal to 1, but it makes it even more simple. The surface equal to pi, but that is the surface of the full circle. So if you have a quarter circle, it's equal to pi divided by 4. You can simply compute it. We already know pi thanks to the ancient Greeks, but what if we didn't know pi? Then we could also estimate it with these Monte Carlo techniques. And I'll show you that. So essentially what we're going to do, so this is what I computed, this is the surface pi divided by 4. And you can also see that the total area here is equal to 1. So this area is equal to 1 minus this thing. And I'm going to show you how, with Monte Carlo simulations, we can also compute this surface area and essentially compute the number required. The value. And that is, again, relatively straightforward. So what we do is we're going to take samples. In this case, we use a uniform distribution. So we essentially mean that any location on this square has the same probability of being sampled. And we do it many times again. And this surface that we want to compute is once again, it's represented by the number of red dots in relation to the total number. So this is how it works, estimating the surface with the Monte Carlo technique. So what is the result of such an experiment? Here in blue we see the true answer, and here in red we see a graph that shows on this axis the number of samples that we have taken, and on the y-axis the estimate coming from this Monte Carlo simulation. And what you see in the beginning, the estimate is terrible. That's because we only have a few number of samples. But with increasing number of samples, you can see it gets closer and closer to the true result. And take more examples, it gets closer and closer. But what you can also see, well, you get a reasonable, decent estimate. You already need about 1,000 or maybe 10,000 samples, which in this case doesn't take that much effort. But you can imagine if you need to, for each sample, you need to do a full hydraulic or hydrodynamic simulation with the model. Yeah, it's going to take a lot of time. So that is one of the main challenges in Monte Carlo simulation. It's very straightforward, it's very useful, but often you are confronted with large computation times. And later we're going to discuss how we're dealing with that in the Brisbane River Catchment study. And I think that's where we are next. Yes, so this was part 1. I explained a little bit about statistical techniques in general and joint probability methods. And now some examples of how we apply these in the Brisbane River Catchment flood study. Well, these are companies involved. So our company is the lead partner in the study, and we are one of the subcontractors, Deltares. Royal Estonian is one, hydrobiology, and Don Carroll project management. So that's Don Carroll, and he hasn't done any project management as far as I know in his project, but he's very valuable. So what is the purpose of the Brisbane River Catchment flood study? I need to add phase 2, so that's the hydrology phase, there are multiple phases. So the challenge is to estimate probabilities of flood discharges, so both peak discharges and flow volumes, at 23 locations all over the catchment for 2 different conditions, no dams and with dams. So in the first case we assume that there are no dams, simulate them and see what are the flows, and then compare it with the current situations where the dams are in place. And we apply 3 different methods. Flood frequency analysis, so that's basically the statistical method where we use extrapolation. Second is the design event approach, where we translate the 1 in 100-year rainfall with the model to the 1 in 100-year peak discharge. And the third one is the joint probability approach. And that's underlined here because that's the one we discussed in the follow-up slide. So the essence of Monte Carlo simulation, I already described it a little bit. So it's essentially 3 steps. The first is to generate a large number of synthetic events, synthetic flood events. The second step is to simulate all these events and to quantify each location and what is the peak discharge in this individual event and what is the total flow volume. And the third step is then to quantify how often are certain levels exceeded at any given location. So the first step is essentially relatively simple post-processing, counting, but especially number 1 and 2 take more effort. So the main challenges is the synthetic events that we generate, they have to be realistic, and they also have to be representative. So a 1 in 100-year event should only happen once every 100 years. We need to look at the data to define, okay, what are the 100-year events, and from that start simulating. And the second challenge is, of course, those computation languages. Now, a number of those challenges, I will have some slides now. One of them is correlation. So, like I said, these events need to be realistic. And that means we need to take correlations into account. And what does that mean? For instance, we have Wivenhoe Dam and Somerset Dam. Well, you can imagine if Wivenhoe Dam reservoir is completely filled, it's full, then there's a good chance that Somerset Dam is full as well. It doesn't necessarily have to be, but there is definitely a relation between the two. So there is a correlation, and that needs to be taken into account. And the same holds for initial conditions of the soil. Are they wet? Are they dry? If the Worrell Creek catchment is very wet, then you can expect that Bremer catchment is very wet as well. Now, in order to simulate that, we have some statistical methods to do that. And what we did is we looked at the data. In this example, we looked at initial losses, initial conditions. And we compared the results that were made available by SCP Water for each of the catchments. And what you now see there is, in this case, there's quite a good relation between the initial conditions in the upper Brisbane catchment compared to the one in the lower catchment. Right? So here you can see you have high losses in one, and there's a good chance you also have high losses in the other. And that we need to take into account. But not just for these two, we need to take that into account for all the combinations, pairs of catchments. So it makes it quite complex. Where you can imagine you fix the correlation correctly for this combination, and then you ruin it for the other. But fortunately, there are some methods available to deal with this, looking at correlation between multiple variables, and we apply the so-called Gaussian CoP for whoever knows that or wants to know more about it. Google Gaussian CoP, or approach me after the presentation. There we go.
It's getting tired.
Yeah. So, are we back in the beginning now? Yes. Okay. The second challenge is related to the computation time. This is one of the joint probability methods, one of the Monte Carlo methods that we looked into. It's called the CRCH method, abbreviation. This is a method that has been applied here in Australia, has been developed here in Australia. And there's a publication of Mr. Rama in the Journal of Hydrology from 2002. And one of the things I present here is the variation you see here. And the reason, what you see here is this method was applied to catchment 5 times. You see 5 lines. So there are the results of each of these simulations. So nothing was changed in between. So the variation really comes due to the random character of the Monte Carlo experiment. You see a big variation, especially here, and that's because these are the very extreme and rare events. So if you do a simulation of 1,000 samples, you can imagine such an extreme event only occurs 1 time. But it can also happen that you accidentally drop 2 times, or 0 times. That means that for the extreme events, because you have so little, there are relatively large difference in outcomes. So that was one of the main problems with the Monte Carlo, and you can solve that by either doing 1,000,000 samples instead of 1,000, but then you need to have a year just doing 1 computation. What we did is we applied a different technique. It's called importance sampling. And importance sampling means you essentially manipulate the distribution that you sample from in such a way that you increase the number of samples of the extreme event. And of course you cannot just do that. You need to apply a correction afterwards for this manipulation. And the correction needs to be such that in the end you have an unbiased result. And this method really worked very well. As you can see in this picture, what we see here, so in black, we repeated the experiment from the previous slide, so with the straightforward Monte Carlo method. And there again you see this effect with large variation in the results. But when we apply reported sampling, you get the results in red. There are also 10 different simulations, but you see each time you get more or less the same outcome. So you have two big advantages of this method. First is that you, each time you repeat this experiment, you get the same result. So it leads to a very small error introduced. And the second advantage is that you, as you can see, you can also have results for much more extreme events. And it's also because when we changed, you kind of manipulated this sampling method in such a way that we have more extreme events. So it means that we also have, we can extrapolate